It's time for another amazing chemistry video with Mr. Stapleton. Grab this one, sit back, I'm enjoying a nice coffee.
Hi guys, welcome to the second video for the organic chemistry topic. This one's going to be all about alcohols. Alcohols are generally just alkanes with a OH functional group on them. That's the simplest way to think about them, but they're a lot more complex than that in real life generally. The first four members, which you can see here, so we've got methanol, ethanol, propanol and butanol. What we can see is that they differ by adding a CH2 group each time. They have that functional group on OH on it. So what it actually looks like, if I've got the ethanol molecule here, and we're going to be focusing on ethanol a little bit more, is you can see the black and white carbons. So we've got hydrocarbons in there, which are non-polar. But you can see we've got the red oxygen in there, and I've tried to show the bonds a little bit differently for the carbon to oxygen bond and oxygen to hydrogen bond, because those bonds are quite polar. The oxygen is quite electronegative, and what that does is that actually allows the bond here to be quite polar, and also this one as well. The oxygen draws a lot of electron density away from the carbon, right, makes that quite delta negative, and also from the hydrogen makes that quite delta positive. So you can actually get hydrogen bonding occurring off of this hydrogen and from other ethanol molecules to that oxygen. So that functional group is quite a different change from just a standard alkane, and it makes an alcohol quite reactive. It also makes it quite soluble in water because of that ability to hydrogen bond. However, as you start to increase the carbon chain length, so as you get more and more of these as they go along, that decreases the solubility because you start to get quite a large non-polar section over here, and you've got this really small polar section up the top. Now, the boiling point, because of that hydrogen bonding, is higher than their corresponding alkane, and the number of OH groups in particular really has a basis or an impact upon the boiling point and melting point. So what I'll do is I'll just bring up my pointer here, if I can get rid of that, and escape. Over here you can see an OH group that we've got here, and you can see hydrogen bonding. Remember, hydrogen bonding is a bond between a hydrogen attached to an electronegative oxygen and another oxygen or nitrogen. We show it by a dotted line because it's a secondary bond. It's not as strong as a primary bond. So you can see this hydrogen bonding occurring between methanol molecules here. You can have a look down here. Ethane, C2H6. Alright, has a boiling point of minus 88.6, so it's a gas at room temperature. As soon as you introduce an OH group and get that hydrogen bonding, your boiling point goes up to 78.3 degrees Celsius, so it's quite a significant increase. Okay, if you add two hydroxyl groups in, so you can increase the amount of hydrogen bonding even more, your boiling point goes up to 198 degrees. Okay, so the strength of that hydrogen bond really has an impact upon the boiling point. Now there's three types of alcohols. There's what we call a primary, a secondary and a tertiary. Okay, so a primary alcohol has two hydrogens, or two or three hydrogens attached to the carbon, which has the OH group. The other way to think about it is that it's only got one carbon attached to this carbon that has the OH on it. Alright, so this is really the important carbon to think about. Okay, this is the one where we need to be able to get to do some reactions. Okay, that carbon there only has one here. Now, R in organic chemistry stands for any sort of carbon chain length, so this is generally just a carbon-hydrogen chain over on the side here. So a primary alcohol only has one carbon attached. A secondary alcohol, you can see here, has two carbons attached to that carbon that the OH is on. A tertiary alcohol has 1, 2, 3 carbons attached to it. You see there's no hydrogens on that carbon. Right? And that's really important when we get to reactivities. Okay, it's said here it's much harder to react with the tertiary alcohol group as the rest of the chain blocks it. So all of these bits around it stop you from getting into the middle. Okay. So alcohol is probably one of the most commonly known things they're known for is oxidation. A test you can often do for alcohols is oxidizing them with acidified dichromate solution. Now, acidified dichromate, or dichromate I should say, is orange in colour. Right, it goes through some colour changes. Dichromate is orange, the chromate ion is yellow, and then you get to chromium ions, which are green. So when we undergo oxidation of a primary alcohol, okay, or a secondary alcohol I should say, that colour change of the dichromate is from orange to green. Now, primary alcohol actually goes through a two-step formation. It firstly oxidizes to an aldehyde. Okay, so you can see the difference in the functional group here to here, and then that aldehyde continues to oxidize to a carboxylic acid. Alright, so there's two possible products out of primary alcohol oxidation. The key thing is to be able to understand the color change from orange to green. The other thing that you need to be able to do is to be able to write half equation as well. So if you suggest I might do it for you again here. Make sure you can do this half equation. So Cr2O7 2 minus, I'm going to be doing it quickly here, plus 6 electrons plus 14H plus. Okay, gives you your chromium ions, 2 lots of Cr3 plus, and 7 lots of water. I apologise for the mouse typing there. Okay, but that's the half equation for the dichromate. It's a reduction because this is an oxidizing agent, so it is in self-reduced. It's a gain of electrons there. You can see sometimes what we do instead of doing those big equations is we actually do what's called an annotated equation. So the annotated equation for oxidation of an alcohol is this, going from a primary alcohol here. This is just the reagents. We use the conditions for the oxidation, so we use H plus and we use dichromate, okay, and we get our aldehyde and then we get our carboxylic acid. Now the reason it needs to be acidified is that we actually need H plus for the half equation. I'll show you an example of that on the next slide when we look at secondary alcohols. But this reaction of an alcohol to a carboxylic acid is quite important in the wine industry, and obviously South Australia, one of the leading exports we have here is wine. And what can happen is if wine is left out or exposed to air, it picks up an oxygen molecule and actually forms the carboxylic acid form. Now, because the majority of all alcohol is ethanol, which is this one here, so this molecule I was showing earlier, right, so that's ethanol. What happens is it picks up oxygen and it actually goes to form this, alright, which I'll actually show on the screen for it, which is carboxylic acid. Alright, so this is alcohol, alright, what you find in your drink. This is vinegar. Alright, basically this tastes alright to drink. Alright, this one, vinegar, tastes not so good to drink. Okay, obviously neither of these compared to Farmers Union Iced Coffee, but obviously if you're a wine drinker, you want to be drinking this, you don't want to be drinking vinegar. So that's why wine bottles always need to be kept with a lid on. Quite often you'll find the best wine normally has cork in it. That's because the cork stops any oxygen going in, and you'll find that they're stored, the wine bottles are stored horizontally like that. And what that does is that allows the wine to stay in contact with the cork at the end. That keeps the cork moist, which when a cork is moist it expands, and that helps it to block the entrance. If that wine bottle is stored upright, the cork becomes dry. When cork gets dry, it shrinks, and that would allow oxygen to come in. So it's really important that you don't get that in there, because it will spoil your wine and ruin the taste. Secondary alcohols also oxidize. It's still able to get in to that carbon and react, but this time instead of going to a aldehyde and a carboxylic acid, they go to a ketone. That's because this secondary alcohol is in the middle of the chain, so you end up with a functional group that's in the middle of the chain. So isopropyl alcohol, which is a very, very common cleaning agent, it's quite good because it's got polar section here, but it's also got non-polar methyl groups on there, so it allows it to dissolve both polar and non-polar materials, or organic and non-organic materials. When that oxidizes, that's formed acetone. Now, acetone is a key component in nail polish remover. It's a really good organic solvent. But again, with the oxidation, there's a colour change from orange to green using dichromate. And at this time, you can see the half equation I've put in. So you can see that there are H plus ions there coming out, and they get picked up by the dichromate. And you need H plus in solution for this actual reaction to occur, which is why we use acidified dichromate. Tertiary alcohols do not undergo any oxidation reactions. All right, there's no hydrogen atom to remove, and there's too much what we call steric hindrance. Those other groups block it. So when you do your oxidation of your alcohols, here we've got a primary alcohol, we've got a secondary alcohol, and we've got a tertiary alcohol. When you do it with acidified dichromate, you can see that we get orange colour from the chromium, but we stay at our orange colour, a green colour from the chromium ions here after we've oxidized it, but here the dichromate is still orange because there's no oxidation that occurs. Okay, I think I need to go get some iced coffee in a minute. So reality is you can tell what sort of alcohol you've got by doing a couple of simple reactions. So if you're trying to work out if it's a primary, secondary, or tertiary alcohol, first of all you add your acidified dichromate solution and you probably warm it a little bit to help increase the rate of a reaction. If it stays orange, straight away you know you've got a tertiary alcohol, so you don't need to do anything else. If you get that colour change though from orange to green, you've either got a primary or a secondary. Now there's two things you can do. To some of the sample of it, you can add something called Tollens reagent. Tollens reagent is ammoniac or silver nitrate, and that will give a very clear silver mirror precipitate, which will very clearly tell you that you had a primary alcohol because you had an aldehyde somewhere in there. The other thing you can do is react with something like sodium bicarbonate. Sodium bicarbonate will give effervescence of CO2 gas with the carboxylic acid that was formed from the oxidation. So both of those you can do to determine if it was a primary alcohol. If you don't get a reaction with either of those, either with the Tollens reagent or with the sodium carbonate solution, you must have had a secondary alcohol. In the exam, they love putting questions in about how you would distinguish between two chemicals using chemical reactions, so this is a really good slide to sort of refer back to. Alright, hopefully this has made sense for the alcohols. There are some videos that I've done around alcohols, primarily around naming them and drawing them, and also oxidation of alcohols. I suggest you have a look at that for a little bit more in depth if you want. But as always, if you've got any questions, just ask. Thanks guys.